This problem is about the following matrix. It's the 2 by 2 matrix A, where the first row is 1, 0, and the second row is 1, 3. And part A says, give the eigenvalues of A. Part B says, find a basis for R2 consisting of eigenvectors for A. Part C says, give a diagonal matrix D, an invertible matrix P such that A equals PDP inverse. Do not calculate P inverse explicitly. And part D says, give a simple expression for A to the 10th as a product of other matrices, not including A itself. Give the entries of your matrices explicitly and make your expression as simple as possible without doing excessive arithmetic or finding inverses. Well, take a few minutes. This should take maybe about 10 minutes. And work on it, and then we'll go over the answer. Let's go over the answer. Making sure I'm recording. Yes. Okay, give the eigenvalues of A. Well, right now I see that this is a 2 by 2 matrix. Normally, to give the eigenvalues of a 2 by 2 matrix, what do we do? You would find a characteristic polynomial and find the roots. And for a 2 by 2 matrix, there's a nice little formula for it, which is lambda squared minus, so the characteristic polynomial is lambda squared minus the sum of the diagonal entries, so it's minus 4 lambda, and then plus the determinant, so plus 3. The determinant is 1 times 3 minus 1 times 0, which is 3. So this factors as lambda minus 1 times lambda minus 3, and when you set this equal to 0, which is what you do to find the eigenvalues, right, they're the roots of the characteristic polynomial, you get 1 and 3. Alternatively, you could also see that I don't have just a random 2 by 2 matrix, I have a 2 by 2 matrix where I have a 0 on the top right. So this is what's called a lower triangular matrix. And when you have a matrix like this, the eigenvalues are actually just the entries on the diagonal, which are 1 and 3. So that's also fine. Okay. Part B says, find the basis for R2 consisting of eigenvectors for A. So I have to find 2 eigenvectors for A that span R2. That's what I have to do. And what's going to happen, since I have 2 distinct eigenvalues, I'm going to have an eigenvector, a one-dimensional eigenspace for lambda equals 1, and a one-dimensional eigenspace for lambda equals 3. So how do I find these eigenvectors? The best way is probably just to calculate the null space of A minus lambda I for each lambda. So for lambda equals 1, I'm going to get A minus 1I, so that's A minus I, so I'm going to get 0, 0, 1, 3. So what I'm trying to do is I'm trying to find one vector with the property that if you take this matrix and multiply this matrix by that vector, you get 0, 0. And the easiest way is to just look at the matrix because it's so simple and figure out what would work. And you can see that one vector that would work is 3, negative 1. Do you see why 3, negative 1 would work? Because when I multiply, okay, when I do 0, 0 times 3, negative 1, I'm just going to get 0, right? And then when I do 1, 3 times 3, negative 1, because I reversed the numbers and then put a negative 1, when I multiply them, I'm going to get 1 times 3 plus 3 times negative 1, and that's 0. So my V1 can just be 3, negative 1. Of course, there's lots of different possibilities, but they're actually all going to be scalar multiples of 3, negative 1. Okay, and remember that an eigenvector is a non-zero vector, so it can't be 0, 0. Okay, and then for lambda equals 3, you just do the same thing. A minus 3i is negative 2, 0, 1, 0. And we have to come up with a v2, and so vector v2 such that a minus 3i times v2 is 0, 0. And it looks like 0, 1 is going to work, right? The first component has to be 0 in order for the product to be 0, the 0 vector. So my basis is going to be 3, negative 1, comma, 0, 1. This set of two vectors. Again, there's lots of different possibilities, but you're going to have one vector which is a scalar multiple of 3, negative 1, and another vector which is a scalar multiple of 0, 1. Okay. Part C, give a diagonal matrix D and invertible matrix P such that A equals PDP inverse. Do not calculate P inverse explicitly. Well, that's easy once you do A and B, because D is going to be the diagonal matrix where you have the eigenvalues as the diagonal entries, so 1, 3, 0, 0, and then P is going to be the matrix where you put the eigenvalues, and as long as you put it in the right order. So since I put 1 as the first diagonal entry, my first column has to be an eigenvector for lambda equals 1, so I put 3, negative 1, and then my second column is going to be an eigenvector for lambda equals 3, which I found 0, 1. So there you go, that's D and that's P. And again, there's going to be lots of different P's, because you can take any, like you can scale the first column and you can scale the second column by anything you want, as long as you don't get 0, 0, and that will also work. Or you could, you don't have to put 1 on the top left and then 3 on the bottom right. You could do 3, 1, but if you do 3, 1, you just have to make sure that you make the matrix P, the order in which you put the columns, match the order that you put the eigenvalues. So if you did D equals, so another possibility would be something like D equals 3 and 1 in the diagonal, and then P equals 0, 1, 3, negative 1. That would also work. Okay. D, give a simple expression for a to the 10th power. Okay, so hopefully you know that when you have PDP inverse, one of the reasons why you care about diagonalizing a matrix is to make it easier to calculate powers of a matrix. And if you do a to the 10th power, it's going to be P times D to the 10th power times P inverse. And give the entries explicitly without calculating inverse. Okay, so you take P, which is this matrix, and then D to the 10th power, and when you raise a diagonal matrix to the 10th power, you end up just raising each of the diagonal entries to the power. So you're going to get 1, and then 3 to the 10th on the diagonal. That's the thing about not doing excessive arithmetic, like not doing 3 to the 10th power. And then P inverse. And the question says you don't have to find the inverse. Hopefully, if you had to find the inverse, you would know how to do it, because it's the inverse of a 2 by 2 matrix. But the question was just asking you to write this out. Okay, so that's a fairly standard computational problem involving diagonalizing a 2 by 2 matrix.